going to talk about today is ionic bonding. The first thing we want to do is try to define what ionic bonding is. So ionic bonding is the electrostatic attraction between oppositely charged ions. And the strength of ionic interactions depend on two things. And the things that they depend on are the charge of the ions and the size of the ions. And by size, we're really going to be referring to the radius. So when we're looking at this, we need to have a relationship, and that relationship that we're looking at is Q1 times Q2 over D, which is Coulomb's law, and we've seen that several times before. So we need to just make sure we know what each one of those variables stands for. So Q1 is going to be the charge on one ion. Q2 will be the charge on the second ion. So with Q1 being one ion and Q2 being the charge on the other ion, D is the distance between the center of the two ions, where D is going to be equal to the radius of the cation plus the radius of the anion. So the strength of those interactions are going to determine the physical properties of ionic compounds. So some of those properties would be that they're brittle, they have high melting and boiling points, and 3, that they're able to conduct electricity if they're molten or if dissolved in water. So the strength of ionic compounds comes from the sum of all of the attractions in the ionic lattice. And you'll recall when we were looking at the video of sodium and chloride, we said that I would have a sodium attracted to chlorines on all sides, even in back and the front, with the alternating pattern like that. So when I'm looking at this sodium, it's hard to see if it's attracted more to that one or that one or that one. So when we're looking for the formula of an ionic compound, we have what we call the formula unit, and it is the lowest whole number ratio. So in this case, it's going to be NaCl. So ionic compounds are composed of metals and nonmetals, or metals and polyatomics. And even though there's ions, all ionic compounds are neutral. And we always put the cation first, followed by the anion. So the next thing we want to do is look at and see how we can compare the strength of ionic bonds. That is, rank the strength of their bond that they have. So we're going to be looking at the factors that influence bonding, and that's going to be charge and distance, And again, we're going to be using Coulomb's law to make some comparisons. So what we're going to do is to compare a couple of compounds. So we're going to rank lowest to highest melting point: magnesium sulfide, magnesium chloride, and sodium chloride. So it's kind of easiest to look at a chart where we have NaCl, MgCl2, and MgS. So Q1, Q2, and we'll figure out what their melting point is, right? Because when we're looking at this particular group, we are looking at similar sizes, but different charges, right? So the sizes are going to be the same. So if I'm looking at the charges, I'm going to have a +1, -1, a +2, -1, and a +2, -2. Remember that if you have magnesium chloride, you never count the two chlorides that give the formula unit. It is just the interaction between one cation and one anion. So go ahead and rank those, and then I will write the melting points for us to compare and see how close you came. So when we look at the melting points that I looked up, don't expect you to know those, but you could do relative ranking. We find that sodium chloride, which has +1, -1, is 800 degrees Celsius. +2, -2 gives a larger attraction, 1412 degrees Celsius, and +2, -2 is 2227 degrees Celsius. So the charges really make a huge difference in terms of increasing that melting point when you increase the charge. Now let's look at another set of compounds. So this time we are going to rank from lowest to highest melting point again, and we are going to be ranking the compounds of KBr, KCl, and NaCl. So when we look at these compounds, we can see that they have the same charges, but they are going to be different sizes. So we're going to not be looking so much at the potassium, but really looking and seeing how the size of the Br compares to the Cl. And then in this case, we'll be looking at the size of the K versus the sodium. So it turns out that these are the boiling points. So if I have a larger ion, and bromine is below chlorine in the periodic table, so it's going to have a higher radius. So a bigger number on the bottom is going to give me a lower melting point. So you would expect potassium chloride to have a higher melting point than potassium bromide, and it does. And then if I have sodium smaller than the potassium, it's going to be even larger again. Notice these are small differences, but they do change the melting point. So that kind of brings us to the end of ionic compounds. You should be able to look at different compounds and rank them according to their strength of attraction, which is then going to show up in their physical properties, such as the melting point and the boiling point.